Hello everybody and welcome back to Environmental Science 101. Section 2 here we got water chemistry. Awesome. So just in brief, I know we may not have all the chemistry here. We don't necessarily need to, right? This is going to be about half of the section right here. We start off with water. Water is constantly splitting itself into these other things, right? One of which acts like a sort of weak acid, very weak acid. This thing that acts like a very weak base. And it's doing this constantly. So we have little bitty weak acids and weak bases in water all the time. Cool, we've got it. Section over. Okay, well, maybe not. Ions. All right. Going to be these little, I don't know, you can think about them as being balls, right? Positively or negatively charged balls or little particles that float around in the water and do stuff, all right? You might imagine, right? So you take a glass full of water and you pour some salt in, right? Salt disappears. What has happened is that the water molecules have broken each particle of the salt apart into Na plus and Cl minus, right? Which are going to correspond to these two, right? Plus and minus. We don't have to worry about these terms. We don't have to worry about electrons. We got to know that there are these things called ions, which are elements that have a charge and exist as little pieces inside of water. And if we got that, that's going to be all that we really need. Awesome. pH. So we might be broadly familiar with pH, learned it in other contexts, right? It applies for soil, it applies for water too. Actually, to kind of connect things here. So pH of the soil is really the pH of the water in the soil is what we're measuring, but sometimes it's easier to think about these as being separate. Awesome. So it's going to be a key parameter for water, right? Determining how acidic or how basic it is. Alkaline means basic. Sometimes you'll see it referred to as caustic, C-A-U-S-T-I-C. Just means basic. These things all mean the same thing, right? 7 is neutral, right? It's where water is. Blood is just a little bit higher. And as a fun or maybe terrifying fact, your blood has to be at about 7.3 to 7.4 pH in order for it to metabolize glucose, right? And make energy for the cells. If at any point your blood pH moves even slightly out of that range, you will go to a coma and probably die, right? It's really, really important. Now, your body has a billion different incredibly complicated, smart ways of making sure that the pH stays there through these systems called buffers, activity of the kidneys, and all this other stuff, right? But pH is really, really important to get right for setting other reactions at the right pace. At least for biology, right? Okay, 7 is neutral, right? 0 on the scale, kind of counterintuitive, right? So low pH is more acidic. So 0 is like battery, right? 1 is like your stomach acid, which thankfully you cannot feel or else that would hurt. Ouch, right? Bleach and cleaning chemicals up here, going to be like 13, 14, right? As basic as it gets. And it's not always going to be the same as danger. What do I mean, right? Like lemon juice, right? Really, really acidic chemically on this scale, but which is more dangerous, right? The lemon or bleach? Bleach is way worse. Like, stuff that is on the basic side is actually far more harmful and dangerous to human beings in a lot of cases, as opposed to acids, even though acids are what we have the fear of, right? What we hear about, right? Okay. Hardness, right? We did pH, now we have hardness. These are related, but we don't have to fully understand how yet. All right. So this is a measure of the amount of dissolved magnesium, right, ions, and calcium ions in the water, right? So just to visualize it, right, and we got these little balls, they got a charge, right? So softer water is going to have very few of these. Hard water has highly concentrated, right? Many of us here in the valley, right, have heard that we have hard water, and now we can know exactly, specifically, what that means. Other places have much softer water, right? So when rain comes down, it is free of these stuff. It would be completely soft, like basically none of these at all, right? But when it hits the ground, it starts to leach in minerals, right? Stuff dissolves from all the minerals in the soil, right? It leaches down into the groundwater, it moves into streams, right? And takes all these things in with it, right? And as a result, tends to get harder, right? Now, we have exceptionally high hardness here. Just for the scale, it's weird, right? But white and red are going to be the highest on here, right? So in Arizona, we are like right here, ish, I want to say. So some of the hardest water in the whole country, and broadly speaking, it's all true in this region. Now, if you notice to yourself that this lines up very well with the precipitation map, then you've kind of made the connection, right? Is that if you have low precip, right, then water that does come down tends to leach out a lot of stuff. In other words, we're not breaking stuff down. We're not carrying minerals away at the same rate as you do in, Oregon, where it's raining constantly. Minerals tend to build up. Water comes down, tends to leach a lot of minerals into it. Happens all the way into our water systems at home. Dissolved oxygen is our next, right? We've looked at this a little bit when it comes to anoxia, right, and the problems with algal blooms and how they absorb all the oxygen and lead to this dissolved oxygen being really low, which kills fish, right, with that fertilizer runoff algal bloom idea. Coming back here, right? So oxygen dissolves into water. It's just a little bit, something like 3 parts per million is what ppm stands for. So in other words, if you were to take 1 million individual particles and molecules out, right, 3 out of every million being oxygen would be a low amount. 5 might be kind of the minimum for fish, all the way up to 10 tends to be like really, really good, can support a lot of life. So oxygen dissolves in from the atmosphere. More of this is better, right? And we want the water to circulate so the oxygen can get where it needs to go. And the fish, right, whenever they swim around, are literally pulling the oxygen out of the water with their gills. It's also why they have to keep moving constantly, right? It's their equivalent of breathing. Broadly speaking, more dissolved oxygen is going to mean more life. Places that don't get good circulation, right, like swamps, lagoons, right, what happens is that when stuff dies in there, or stuff dies on land and falls in there, it absorbs all the dissolved oxygen that's in the water, right? And then since there's no circulation, it's just gone, right? And so a lot of times you'll wind up with these bottom parts of the lagoon that have no oxygen at all. It's actually part of how things like coal form, because stuff gets buried and then processed later without being destroyed by oxygen. Awesome. Okay, nitrites and nitrates. So we talked about the nitrogen cycle a little bit, and here it comes back up in kind of a different form, in aquatic form. So we talked about how important these are and how plants really love them in these forms, right, and sucking them up, but broadly speaking, things besides the plants don't necessarily love these, right? This stuff, especially in water or in the context of aquatic life, is usually going to be bad. We want to keep nitrates and nitrites low for fish, and we want to keep them low for human beings. Gets into water in all sorts of different ways, so it can come in from sewage or septic tanks, other sorts of waste, things like landfills. It can come in from fertilizer or just stuff dying, right? And compounds are turned into these forms. But, right, unlike with plants, we don't want these. Awesome, we know it. Heavy metals, right? Not the cool kind of heavy metal, right? This is the kind of dangerous kind, right? This is the poisonous kind that you do not want, right? So these are going to be heavy elements on the periodic table, right? So we imagine like our nucleus of the atom, right, with all the little balls in the middle. This is going to have a lot of those little protons and neutrons, big individual atoms, right? And broadly, right, these are all going to be bad for human beings. We don't want these. The body needs these elements, like the tiniest amount, but if it's got any more than what it needs, it can cause problems, right? It can poison people, make them sick. I have the WHO limit here, so here comes parts per million, ppm again, like with dissolved oxygen, right? We see that the limit is really low on a lot of these, all right? So if you have 0.001 parts per million of mercury, that's considered to be too high, just to give an idea of how dangerous this stuff can be for human beings. There's a lot of different metal ions that can kind of come into this list. We group them all together, right? Because they are chemically similar, they're regulated in similar ways, come from similar sources for a lot of them, and because they're pretty much all bad. A lot of sources on this, stuff like electronics and e-waste or in landfills can seep into water and get there. Can be pulled out of pipes. Famously, in the case of Flint, Michigan, where there are issues there, we will get to in a case study. It can also come in from minerals, right? Just out of the ground. If you have some deposit of a mineral that includes mercury or something, it can seep in over time. Chlorine is going to be our next one. Now, many of us are familiar with chlorine in the form of pools, and that's the gist, right? It acts as a disinfectant, right? So, kind of a trade-off here, right? So chlorine being added, if you go way back, like 1900 era, right, or even before, killed off a lot of infectious diseases in water. That is good. This saved lives. This is a good thing. Trade-off is that the chlorine itself is not really good for people, right? So we don't want more than about 4 ppm. This is something that you definitely don't want in your water, right? So water that comes into your home, right, is going to pass through water quality checkpoints, right, and systems that disinfect and treat the water before it gets to you. And chlorine is going to be part of how they do that. But if too much chlorine is left after the disinfecting process is done, it can get to you. You don't want to drink it. It's, broadly speaking, not good, and actually cause a smell too. We don't want this. Pharmaceuticals, right. So we could talk about this a lot. I'm going to give you the kind of long story short version of it. All right. So this stuff getting flushed down the toilet, or waste from manufacturing, or all the different ways, right, they can enter the water system, right, or even being dumped on the ground, right, gets into the environment, gets into animals, gets into drinking water. And with this stuff, even in very small amounts, as is the case with synthetic stuff, right, really, really small amounts can still have an effect. For the most part, this is not going to be something that we have to worry about, broadly speaking, but at the same time, right, we want to make sure that we're treating water, we're filtering it so that this stuff doesn't get through. It can be really hard to test for this, and it especially tends to be a problem for animals, smaller mass, right, and especially small predators who eat other animals tends to get concentrated higher up in the food chain. And it can have all sorts of disruptive effects, especially endocrine, especially day-night cycles. And this could be any sorts of drugs, right? Antidepressants, antipsychotics, sedatives, painkillers, right? Essentially anything that you would be prescribed as a drug by a doctor can get in this way. Not good. That's going to be everything that we have on water chemistry for now, all right? So we're going to move from water chemistry and apply that to life and aquatic ecosystems, and then finally get to pollution and contamination in the end.